You already know black holes devour everything that gets too close. So why did three separate clouds of gas orbit the most powerful black hole in our galaxy, pass within 93 billion miles of its event horizon, and come out the other side completely intact? That is not supposed to happen. The physics says it cannot happen. And yet astronomers watched it happen. 3 times, on nearly identical orbital paths, separated by years. The scientists tracking these clouds are concerned, because if these clouds are surviving, it means something about how Sagittarius A behaves is fundamentally different from what our best models predicted. And what they found feeding those clouds toward the black hole at the center of your galaxy right now as you watch this changes everything we thought we understood about how supermassive black holes stay active. By the end of this video, you will know exactly what is orbiting Sagittarius A, where it is coming from, and why the world's leading astronomers are paying very close attention. The black hole at the center of our galaxy is called Sagittarius A star. It sits 26,000 light-years from Earth, dead center in the Milky Way. Here is what 4 million solar masses actually means in terms you can feel. Our sun is so massive that its gravity holds 8 planets in stable orbits across billions of miles of space. Sagittarius A is 4 million times heavier than that. If you lined up objects the size of Earth, each one as massive as our planet, you would need 1.3 trillion of them to equal the mass of this single black hole. Its event horizon, the point of no return where not even light can escape, stretches roughly 15 million miles across. That is about 17 suns placed side by side. And yet, compared to the largest black holes ever discovered, Sagittarius A is considered small. The black hole at the center of galaxy M87, photographed for the first time in 2019, contains 6.5 billion solar masses. A black hole called Ton 618 contains 66 billion solar masses, making it roughly 16,000 times more massive than the one at the center of our own galaxy. By cosmic standards, the black hole we orbit every 230 million years is almost modest. If you are watching this channel for the first time, subscribe to Space Aquarius. We cover the science that most channels won't touch. The story of how we even confirmed Sagittarius A exists is one of the most patient experiments in the history of science. In the 1970s, radio telescopes scanning the galactic center picked up a powerful, compact radio source in the direction of the constellation Sagittarius. It was bright, it was concentrated, and it wasn't moving. Scientists named it Sagittarius A, the asterisk denoting a radio-excited source. Something massive was hiding at the center of our own galaxy, but proving it took decades. Beginning in the 1990s, 2 independent teams of astronomers began tracking individual stars near the galactic center using infrared cameras, the only wavelength that can cut through the enormous clouds of gas and dust blocking our view. One team worked out of the Keck Observatory in Hawaii. The other operated the Very Large Telescope in Chile. Year after year, image after image, they watched. And the stars near the galactic center were moving in ways that defied expectation. One star in particular became the key to everything. Scientists labeled it S2. It completes a full orbit around Sagittarius A star every 16 years. At its closest approach, a point called periapsis, S2 gets within roughly 17 light hours of the black hole. For reference, Neptune sits about 4 light hours from our Sun. S2 gets 4 times closer than that to a supermassive black hole. At that distance, it accelerates to approximately 2 to 3% the speed of light, somewhere between 4,300 and 5,600 miles per second. Fast enough to travel from Earth to the Moon in under a minute. Scientists tracked S2 through one complete 16-year orbit, watching it sweep past the black hole in 2002 and again in 2018. When they ran the math, the answer was unambiguous. Something with the mass of 4 million suns was sitting at the center of those orbits, packed into a space smaller than Mercury's orbit around our Sun. No star cluster could be that dense without collapsing. No gas cloud could hold that much mass in that little space. Only one thing in physics fits. In 2020, the scientists who led this work, American astronomer Andrea Ghez and German astronomer Reinhard Genzel, were awarded the Nobel Prize in Physics for confirming the existence of Sagittarius A star. Another star, designated S62, has one of the shortest known orbital periods ever recorded. completing a full orbit in just 9.9 years and reaching speeds approaching 10% the speed of light at its closest point. That is not a typo. 10% the speed of light, around a black hole at the center of our galaxy. In 2018, researchers also found evidence for thousands of smaller stellar mass black holes clustered within just 3 light-years of Sagittarius A, packed into the galactic core like a graveyard of dead stars. The center of the Milky Way is not quiet. It is one of the most crowded, violent, and active environments in the entire galaxy. Which brings us back to the three clouds. In 2012, astronomers detected a compact object they called G2, a dense clump of ionized gas orbiting Sagittarius A on a highly stretched elliptical path. It contained a few Earth masses of material and was emitting hydrogen and helium light, consistent with hot gas mixed with dust. Its orbit was extreme. G2 was going to pass within roughly 100 times the Earth-Sun distance, about 93 billion miles from the black hole itself. Scientists prepared to watch it get destroyed. The tidal forces near Sagittarius A are so extreme that they should have stretched G2 into a long, thin streamer of gas, a process called spaghettification, and pulled it across the event horizon. That is not what happened. G2 survived. It lost some orbital energy through drag as it passed through the hot gas swirling around the black hole. But it held together. It came out the other side as a recognizable, compact object. The models had predicted its destruction. The models were wrong. When astronomers went back through archival data, they found G1, a similar compact cloud that had passed Sagittarius A on a nearly identical orbit approximately 13 years earlier. Same orbital shape, same behavior, same survival. And then in research published in March 2026 in the journal Astronomy and Astrophysics, a team led by the Max Planck Institute for Extraterrestrial Physics announced the discovery of a third compact cloud, now part of what scientists are formally calling the G123 streamer. 3 clouds, nearly identical orbits, moving in sequence around the most extreme gravitational object in our galaxy. The research team used 2 of the most advanced infrared spectrographs in the world, Symphony and Eris, both mounted on the Very Large Telescope in Chile, to reconstruct the orbits of all 3 clouds using their positions and velocities. The conclusion was direct. The probability of 3 unrelated objects independently arriving on such similar orbits is statistically negligible. They share a common origin. The leading theory from the Max Planck team points to a specific source, a massive contact binary star called IRS-16SW, located in the clockwise disk of young stars orbiting Sagittarius A. A contact binary is a system where 2 stars orbit each other so closely that they are essentially touching. The stellar winds from both stars, the constant streams of charged particles they shed, collide in the space between them. That collision creates a shock wave. Gas builds up, gets compressed, and eventually breaks away as a separate, dense clump. Computer simulations run by the research team show that these clumps can form exactly this way, and their predicted orbital paths match what astronomers are actually observing in the G123 streamer. The slight differences in the orbits of the 3 clouds can be explained by the binary star's own motion over time. If the models are correct, IRS-16SW has been quietly manufacturing gas clouds and feeding them towards Sagittarius A for an extended period, acting as a slow, steady supply line to the black hole at the center of our galaxy. Scientists estimate that if one clump falls inward roughly every decade, carrying approximately 1 Earth mass of material, that is enough to sustain the current level of activity at Sagittarius A. These clouds may be the fuel that keeps the galactic center running. Not everyone agrees on this explanation. Some researchers have proposed a different origin entirely. Their theory suggests these clouds could be produced by protoplanetary disks surrounding young stars that get scattered too close to the black hole from the observed ring of young stars orbiting Sagittarius A star. As those stars approach the black hole, the intense radiation and gravitational tidal forces strip away the disk material, a process called photoevaporation, producing compact clouds of gas that then follow the star's orbital path inward. This model carries a striking additional implication. If it is correct, it means planets are actively forming near the center of the Milky Way, and that the debris from those disrupted planetary systems can reveal the presence of stars that are otherwise too faint for our telescopes to detect directly. Other scientists have pointed out that massive stars near the galactic center frequently form in groups, and that recent research confirms most massive stars are born in triple systems. A triple star system tidally disrupted by Sagittarius A could explain why 3 clouds are following similar orbits, rather than just 1 or 2. The debate between the binary star wind model and the disrupted stellar disk model is still open. Both sides agree on one thing. These clouds are not random, and they are actively feeding the black hole at the center of our galaxy. That finding alone reshapes how astronomers think about black hole activity across the universe. For a long time, the assumption was that supermassive black holes were fed primarily by large, dramatic events. Galaxy collisions, massive gas clouds collapsing inward all at once. Big, violent episodes separated by long, quiet periods. What the G123 streamer suggests is something different. The feeding can also happen quietly, steadily, continuously, through small clumps of gas produced by ordinary stellar processes happening just a few light years away. Star formation and black hole activity connected in a single, unbroken loop. In May 2022, the Event Horizon Telescope, a planet-spanning network of synchronized radio dishes stretching from Chile to Hawaii to Arizona to Spain to the South Pole, released the first direct image of Sagittarius A. It showed a glowing ring of superheated gas, its light bent into a circle by gravity, surrounding a dark central shadow, the silhouette of the event horizon itself. The ring spans roughly 52 micro-arc seconds across the sky. To put that in perspective, it is the equivalent of seeing a donut sitting on the surface of the moon from Earth. Sagittarius A was significantly more difficult to photograph than M87 because it is smaller and far more active on short timescales. Gas swirls around it on timescales of minutes to hours, causing its brightness to shift constantly. The EHT team had to synchronize data from observatories across the entire planet, compensate for Earth's rotation, and correct for atmospheric distortion to build the image pixel by pixel. What they produced was the first photograph of the object we have been orbiting our entire lives. Here is the part that most people do not sit with long enough. The light captured in that 2022 image left Sagittarius A 26,000 years ago. When those photons began their journey toward Earth, modern humans were living through the last ice age. The first cities were still 10,000 years in the future. Writing had not been invented. Agriculture had not begun. That ancient light traveled across 26,000 light-years of space, through dust clouds, spiral arms, and the quiet lanes between stars, and landed in our telescopes. What is happening at Sagittarius A right now in this exact moment? We cannot know. The light that would show us today's activity won't arrive for another 26,000 years. The gas clouds spiraling inward, the stars accelerating around the event horizon. Whatever is feeding the black hole at this moment, all of it is invisible to us, separated not just by distance but by time itself. Subscribe to Space Aquarius, leave a comment below telling us which part of this story surprised you most, and share this video with someone who loves space. Because the science happening at the center of our galaxy right now is some of the most important work in modern astronomy, and most people have never heard of it.